Welcome to Math 119, Chapter 3.1, where we're talking about functions and relations. So functions are all around us. So it's nearly every physical phenomenon that we observe in one quality depends on another. So for example, your height depends on your age. I have a little toddler. She's pretty tiny, right? But as she's going to get older, she's going to grow taller and taller, right? So therefore, her height is dependent on how old she is. Or the temperature depends on the date, right? It's really hot here in Charleston, but the further along we get into the fall, the nicer, cooler weather is going to come in. So the temperature is going to depend on that season or that date. The cost of the mailing package depends on its weight. So the heavier that package is, the more it's going to cost. And we can see all of those in different forms of charts. We have a nice visual chart here with height. We have a scatter plot of sorts, and then we have just your standard chart here. Now we can use the term function to describe the dependence of one quantity on another. So that is, let's say, here's some more examples. The number of bacteria is a function of time. So which one of these is the dependent variable? Well, the bacteria, right? The more it's going to grow over time. So your time is the independent variable, right? You can't really cap time. It just goes throughout. But depending on where we start, where we start and stop, the bacteria will continue to grow. Now, the weight of an astronaut also depends on the elevation. The higher and higher we get out of the atmosphere, the lighter we get. The price of commodity depends on the demand of that commodity. Now, if you're at all confused, kind of a tidbit, whatever comes first before the sentence is a function of, the very next thing is going to be the independent value, and the one before it is going to be the dependent, typically. Time, any sort of time value, so that's seconds, months, years, that is always going to be independent. Now, definitions of functions. A lot of our textbooks have very, very wordy sentences that are kind of hard to figure out what it actually means. So for example, this one says a function is a relation between two variables whereby each independent variable in a domain, so all of the x values that are present, maps to one or more dependent variable in the range. That is, domain is a possible set of inputs and range is a possible set of outputs. So if that sentence doesn't quite make sense, right? Domain being your x values and range being your y values, think about shortening that sentence. It's just saying every x has exactly one y. Or it's just saying that your x values do not repeat. If you have repeating x's, that means that it's going to be mapping to more than one dependent variable, which is not okay. And we're going to see a visual aspect of that. Now, we also have arrow diagrams to kind of figure that out. Now, these are your inputs and your outputs. Your inputs being your x values, your domain, and your output being your y value, your range. Now, to read this can be a coordinate. This is just saying, okay, this one maps or goes to 20. So 1, 20 is a coordinate. And then you have your next one, you have 2 mapping to 20, and 3 mapping to 30, and 4 mapping to 40. Now, is this a function? Well, we talked just a moment ago about your x values not repeating. Do you have any x values that are repeating? No. We do see y values repeating, but that's okay if they have a repeat in the y. So this is okay. What's not okay is your x value to repeat. Now, what does that look like? Well, if we have a repeating x value, perhaps something like this, what do you notice which one is going to repeat? Well, your 2 repeats. Your 2 not only goes to 2 and 20, but also 2 and 30. So when you go to evaluate a function, when you say, okay, f of 2 is equal to, well, it can't be both equal to 20 and 30. Which one is the right response, right? We won't know that. So that's why it's not going to be a function. So not a function. Whereas over here, if we put in a 2, we're going to get out a 20. If we put in a 1, we'll get out a 20. If we put in a 3, we get out 30, right? Each x that you put in is going to come out with a y value. So let's talk about domain and range just a little closer. So if the arrow diagram shows a list of coordinates to map one to another, then it also provides us with your domain and ranges. Because keep in mind, these are just a series of coordinates right here. So let's see example 1. Can you state the domain and range and determine whether or not this is a function? Well, your domain is just your x values. So picking out all of your x values, whether you wanted to plot it or not, right? Your domain, we have -4, 6, 0, and -4 again. So these are all of your x values. Now notice what is repeating. Well, you have -4 here listed twice. So it's mapping to 2 and to 0. So is this a function? Not a function. Now, if we weren't really interested in whether or not this is a function, but we were trying to determine its domain, we don't need to account for that repeat since we already accounted for the -4. Doing the same for your range, it's now just your y values. 2, -1, 0, and another 0. Again, there's a repeating 0. So just listing it once. So these will be your y coordinates here for your range, and your domain is your x values. So we said, is it a function? No, it's not. So let's try it again on your next example over here. Now notice you don't have a series of points, or at least points that are given. Instead, you're given -3x plus 7y is equal to 13. Have we seen that structure before? Yeah, back in our video from chapter 2.3 and 2.4, this is a line in standard form. So let's see if we can figure out your domain and range. So if you already know it because it's based on a line, awesome. But let's say we don't know how to do your domain and range in this format, but we at least know how to graph a line. So can we change it into the form y equals mx plus b? Well, we can do that by moving this 3x over. So you have 7y is equal to 3x plus 13. Divide each of these by 7. So we have y is equal to 3 over 7x plus 13 over 7. It's okay if we're dealing with fractions here, but let's say we were trying to graph this particular line. Where do we start? Well, we start on your y-intercept, your b. B is positive, so it's somewhere up here. It's about a little less than 2. So I'll just lower it a little bit. Then what do we do? Well, your slope is 3 over 7. So from this point, we're just going to go up 3 and over 7 to your next point, or down 3 and over 7 to your next point. So kind of getting a visual on what this graph looks like, we can then go ahead and determine your domain. Now, these arrows suggest they continue without bound. So looking at your x values, we go from negative infinity. Our graph is starting way out here from negative infinity, and it's going to travel all the way across your page. And your x values, as they're traveling, are going to get bigger and bigger and bigger. So towards positive infinity. And that's going to be for all lines as long as there's no holes or jumps. And your range, well, same idea, trying to figure out, okay, if this graph starts way over here, right? Well, your y values, they start off really, really small and then they're going to get bigger. So starting small at negative infinity. And as you're traveling up, or sorry, out, you're also traveling up. So you're going to get very, very big. So one more time, from negative infinity to infinity. Now, is this a function? Yeah, this is a function. Because your x values, you're looking at your x values here. Let's just pretend this is, we can plug in a 1, right? Plugging in a 1, and you'll get your y. Plugging it in. Over here, you can see that your y values aren't going to be repeating. And I don't want to give too much away, but there is going to be a test that we can do when it comes to the visual of your graph. So testing a function, it can be easy if a set of coordinates or an equation is a function to kind of determine the aspect of it. Do your x values repeat? But what about a graph itself? So let's, instead of plotting these points, let's actually practice writing the equation or having the equation of a line and having you guys actually graph y equals negative 2x plus 3. Okay, so graphing, we're starting at your y-intercept. So starting at when y is equal to 3. And then your slope, are we going to be increasing or decreasing? Your slope, and we're going to be starting here. Your slope, we are going to go down 2 and over 1. So down 2 over 1 to your next point. And let's say I wanted to do that again, down 2 over 1, down 2 over 1, and we can just keep plotting that same trend of going down 2 and over 1, or perhaps if I wanted to get over here, we can do the reverse, up 2 over 1. And let's connect the dots. So then what is your domain here? And what is your range? Now, just like last time, your domain and your range are going to be all real numbers for both, from negative infinity to positive infinity. Now, is it a function? Well, we talked about last time, lines are going to be considered functions. The reason for that is notice how many points I plotted. And I wanted to do it on this graph because it's a little bit easier to see, right? This is 0, 3, this is 1, 1, this is 2, negative 1, and I'll only do just a few more. Let's see, this is 3, negative 3, negative 1, 5, right? All of these values, all of these points here that I'm putting on, and they extend on either side. Do you notice any x values repeating? No. Do you think that they will repeat? No, if they haven't repeated just by plotting this many points on your graph, it's likely that there won't be any x values repeating. Now, there is a test. This is called your vertical line test, which suggests that we are going to draw a vertical line anywhere on your graph. So drawing a vertical line anywhere on your graph, it doesn't matter, it just has to hit somewhere on your graph. And wherever it meets your graph, if it touches your graph once, then that is considered a function. So that being said, and don't worry, there's an explanation for it on our next page. So don't feel like you have to write all of that down. So I'm going to draw a series of graphs, and just based off that vertical line test, can you determine whether or not we have a function? Let's see. And there you have it. So figure out, do we have a function or not? The vertical line test just says draw any vertical line anywhere on your page that's just touching your graph. So we're just going to do that really quickly. Anywhere on your graph. If it touches once with your graph, it's a function. So is this one considered a function? Yes, it's a function. What about your next one? It hits once, twice, and automatically that is no longer a function. The reason for that is that if you were to pick out this point, let's see, we have -1 and 2. And again, over here, we have -1 and 1, 2, 3, it looks like, -3. Notice that that x value is going to repeat, which is not allowed. Whereas if we did it over here, we just have that 1 point. Let's just say it is -1, 2, -2, and -1/2 or something to that degree, right? There's no other value that it touches. And one more time, is this one a function? Yes. And no. Now, before we wrap it up with the vertical line test, can you also determine the domain? The domain and range for all of these functions. Well, these arrows all suggest that they're going to be continuous and go off the page. So with your domain, right, your domain is looking at your x values. Now, do you have any sort of x value restriction? No, your arrow is not only going up, but it's going out to -infinity. So we start way out there in -infinity. And as we're doing this little V symbol, we go back out towards what value? Towards +infinity. So absolute value functions are going to be -infinity to infinity, are all real numbers for your domain. Now, what about your y value? Is that going to, or your range? Are those going to be all reals, or is that going to be different? Well, range we read from bottom to top. So the smallest y value you see, what is it? It's 1, 2, 3. So we got 0, -3. And then you're starting at -3, and then you are growing up. Now, -3, because we are there, we can have a solid point on your graph here. We're going to include that -3, while we always exclude your infinity. Your domain here, let's try it again. Is there any funny business going on with your domain? Is it all reals, or is it something different? Well, it's going to be something different this time, because your arrows don't extend off the page out here. Instead, what's the smallest x value that you see? Your smallest x value, let's see, at this particular point is at -5 and -1. So this is your smallest x value. There's nothing more negative than this -5. So we start here, and where does your graph go? Well, your x values are going to continue to grow. So they start at -5 and they continue to infinity. In your range, do you have any restrictions? No. So your range, they start not only is this going out, but it's going to get lower and lower. It's going to go further down. So we start at negative infinity. And as we come up towards this special point, we're going to go out, but also up. So we're going to grow to infinity. Now, this is going to be true for all kind of parabolas that are on its side. Your domain is going to be more restricted, and your range is going to be all reals. All right, the last one. It's going to be all reals for both, or from negative infinity to positive infinity. Again, because there's no restriction, it's a nice smooth curve. Your x values, they're going down but out, and then up and out. And same thing with your range. We start down low, we do a little couple twists and turns, and then we finish up high. So kind of to define that vertical line test one last time, we just talked about the vertical line test that can determine if the graph is a function by drawing a vertical line anywhere through the graph. If the line touches the graph only once, then it is a function. If it touches more than once, then it is not a function. Now you might be wondering, okay, if there's a vertical line test, is there a horizontal line test? Yes, there is a horizontal line test, and that is to test for inverses. We're going to be learning that in 4.4, so in just a few more sections. Now, to talk about functions, we also want to work on evaluating functions. So in the definition of a function, the independent variable x plays the role of a placeholder. So for example, if we have the function 3x squared plus x minus 5, we can just replace that x with anything you want. So by doing that, we just leave gaps. And you notice that when I go to write a lot of this stuff, I usually use gaps, and then I put in my x value, whether that's my x or any sort of variable that I want to substitute. You can put anything in you want. Now, if you have a hard time visualizing this, not just with numbers or with other variables, or even a binomial or a trinomial, just replace your x values with parentheses and a gap. So let's go to evaluate this function with these values. So see if you can pause the video and try example 3. So how we can read number A, or letter A, this is saying f of -2. Now normally this is f of x. Normally there's an x here. Now what they're just saying is that what happens to this function when we replace x with a -2? So we're going to just do that exact thing. So again, x used to be here, used to be right here as such. But we're going to erase these x values, and I'm going to copy and paste. I'm going to copy this before I move on, but we're going to replace these x values with now a -2. And then use what you know about your orders of operations. So we have to do the exponent first, so -2 times -2. And then we can go ahead and figure out the rest. So we can have 12. -2 minus 5, that'll make -7. So 12 minus 7 is 5. Now your answer isn't just 5. We want to know, okay, well, what did we have to do to get this 5? So we have to restate that we put in a -2 to get out a 5. So by putting in a -2 into your function, we get out a 5. Now this is a point on your graph. So another answer you can also put is -2, 5. Now let's try it again with these other ones. Again, this is f of 0. So what do we get when we insert a 0 into your x value. So again, leaving gaps, putting in a 0, we get 0 plus 0 minus 5. So f of 0 is equal to -5, or again, the point 0, -5. Either of those answers is acceptable. Now, C and D might be a little weird because we're not actually putting in a value. We're actually just replacing your x with another variable. But the process is the exact same. This is just saying what happens when we switch x to a. So x to a is just as such. 3a squared plus a minus 5. And that's all we have to state, is that we have f of a. Now the point, if you wanted, you can just say a and f of a. That is as far as you could go with that value. But what I'm looking for on a test is this. Doing it again. You're replacing your x with 2a. So leaving those gaps, putting in 2a, and evaluating a bit, we have 4a squared, because don't forget, just because you have your coefficient doesn't mean that it's just going to this a, it's actually distributing to both. Plus 2a minus 5 is equal to 12a squared plus 2a minus 5. Now, what did you get, or what did you have to put in to get this response out? You put in f of 2a. Now, let's have you do it again. At the very least, try a and b in your new function, 3x squared minus 2. Okay, so this time we are inserting an a where your x value used to be. So again, your x value used to be where these gaps are. We're going to replace those gaps with x is equal to a. So putting in an a here, we now have 3a squared minus 2, and that comes from f of a. Let's do it again, now with this binomial, so something a little bit bigger. We have f, what used to be x, is equal to 3, what used to be x squared, minus 2. So we get to replace this whole thing with x is equal to a plus h. A plus h. A plus h. Now, unfortunately, unlike last time where we had a monomial, if these were multiplied together, we could then go ahead and distribute. But because we have a plus sign here, we now have to write 2 of these. We learned this back in chapter 1.3. And again, I want to say that was in 1.2 as well. So now let's go ahead and FOIL. A squared plus 2ah plus h squared. Again, if you do not know how to FOIL, please go back to 1.3 or find some of the videos that are just strictly on FOILing. Let's go ahead and distribute your 3. I do recommend FOILing before distributing, because what happens with a lot of students is they believe this 3 actually gets multiplied to both, but it's really just 3 multiplied to 1 that is then multiplied to the other. 3a squared plus 6ah plus 3h squared minus 2. Now, in order to get this response out, we had to put in a plus h. So let's take a look at C. Now, C is asking us to do a combination of things. It's saying, can you take f of a plus h, which is this whole thing here, and can you subtract what you got from f of a and then divide it by h? So what that's going to look like, and pause the video if you want to write it, is we're taking what we got out from a plus h, we're subtracting what you get from here using parentheses, 3a squared minus 2 divided all by h. So one more time, this is kind of color coordinated so you can see where we're getting these values. And now go ahead, pause the video, and simplify. We're going to go ahead and distribute this negative in and drop your parentheses over here. So you have 3a squared plus 6ah plus 3h squared minus 2 plus, or sorry, minus 3a squared plus 2 all over h. Now what happens in the numerator? Well, now we can go ahead and combine your like terms. So combining your like terms, notice that you have a negative 2 and a positive 2. You have a positive 3a squared and a negative 3a squared. So those cancel. You're left with 6ah plus 3h squared over h. Keep simplifying. What are we going to do? Well, each term has an h, so whether you factor out the h or you can cancel however many that are in common. So you're left with 6a plus 3h. Now, while this is a good and okay answer, there's one better. Can you go ahead and can you determine if it's if you can factor just a little bit more? Factoring is always better. Notice that they have a 3 in common. So we're going to take out a 3, leave behind a 2a plus h. This is the better answer. For me, I don't mind if you are here. This one would be a lot better. Some teachers are going to be a little bit more strict perhaps in the future, but this is an okay answer. Now, if you need help with evaluating, there is a worksheet just on this, kind of this stuff and this stuff over here. So definitely check that one out as well.